right into the fourth and final lecture on applying bosonization to a couple of interesting physics problems in 2 dimensions. In particular, we will solve what's called the Thirring model in 2 dimensions, as well as we will show confinement and mass gap in quantum electrodynamics in 2 dimensions. If you already know, confinement and mass gap for Young-Mills theory is the million-dollar problem. So we will solve a baby version of that million-dollar problem. Okay. Over the last weeks, we discussed the 2-dimensional fermions given by Dirac fermions, and we showed that this 2-dimensional fermion is equivalent to a compact boson. In this lecture, as I just mentioned, we will add interactions. So the first simplest type of interaction that we will try to add is this. We will add a 4 Fermi interaction. So this is called the 4 Fermi or the Thirring. I think Thirring is a person and he studied this 4 Fermi interaction or the Thirring interaction. Famously, this interaction was used by Fermi in 4 dimensions to explain beta decay, but as we might recall from our QFT lessons, that this interaction in 4 dimensions is not renormalizable. So this is in 4 dimensions is at most an effective theory, and then the UV complete theory was the Glashow-Weinberg-Salam model. But in 2D, this interaction is perfectly alright, it's renormalizable. If we do a bit of dimensional analysis, we can find that the coupling constant G has no dimensions, it's just a pure number. Right. Now, what that means is that this is a fully interacting theory and fully sensible, fully interacting theory. Normally what we would do is to try to solve this. Oh, by the way, we can also add a mass term if we want to. With the mass term, it's called a massive Thirring model. So usually what we would try to do is to solve this for small g perturbated. But it turns out that with this bosonization that we studied, this model can be solved exactly. So we will solve this model exactly as a warm-up to QED2. Alright, so let's recollect bosonization. So this is a recap. Last week, with a bunch of caveats, we found that the chiral fermion, psi minus, so remember this is a Dirac fermion with 2 components, and these are called the chiral fermions. The chiral fermion, if I map it to 1 by 2 pi root 2 pi epsilon normal order e to the I phi minus and psi plus to 1 by root of 2 pi epsilon e to the minus I plus, where phi is a compact boson with radius equal to 1 by 4 pi. So just a quick recap, compact, this means phi plus 2 pi is identified to be the same as phi, and the action for the boson was beta we call the radius of the boson. So if the beta has this particular value, then by making this identification, we can map correlation functions of one theory to the other theory, and they match exactly. So
What's the epsilon?
Epsilon is the UV cutoff. Epsilon is 1 by lambda is the UV cutoff. Lambda is the UV cutoff. Epsilon is the lattice spacing or something. Right. So we derive this by matching correlation functions on both sides. Right. Now, as we see, yeah, I can skip this. As we see here, the interaction in the 4 Fermi theory is nothing but a current-current interaction. So for the fermion, we had the U1 symmetry that you can rotate the fermion by a phase, and that results in a current that we call the vector current. So this is for the fermion. And that was psi bar gamma mu psi. We did this maybe in the first lecture. And we are going to try to bosonize this model. So the interaction we are interested in is the current-current interaction. So we will find what this current is under the bosonization map. Alright, so if we make use of our conventions for what gamma mu's were, we can directly calculate the 0th component to be just say that the psi plus minus psi minus, just like number operators for left-handed plus number operator for the right-handed fermions, and the one component is, the sign's wrong.
Should the first 10 balls have daggers?
Hmm?
First 2 tennis balls should have daggers?
No, made a mistake, thank you. So this plus and dagger, when I write it,
Yeah.
so plus and dagger. This is simple algebra that I'm skipping. Gamma mu's where, sigma 0, sigma 1, sorry, sigma 1, sigma 2, etc. And we can do that matrix multiplication and just find this. Okay, so what we need to find is what this operator is, and this operator is under this bosonization map. Here we have to be a bit careful because these two operators are defined at the same space-time point. And like we saw last time, when operators coincide in their space-time points, we get infinities. So we have to be careful in defining this. And we'll be careful by defining it in a way that's called point splitting. So we will define, for example, psi dagger minus, psi minus, both evaluated at x. This is a composite operator evaluated at x, and we will define it to be limit y going to x, minus x, equals 1. We will define it by splitting the point and taking the limit at the end. So we will see at the end that.
Is it one-sided limit? Does it matter whether y is greater than or less than x, or does it work in either order?
I think it doesn't matter. So we will see in the end that if we did not do this, we will just get infinity for this composite operator. So let's do that. So let's bosonize that. So under bosonization, and we know bosonization map using this arrow, we will get 1 by 2 pi epsilon, and remember minus was e to the I phi minus, so we would have e to the minus I phi minus at x times e to the I minus at y. And this 2 pi epsilon was a common factor. Alright, now again exercises from last week. Product of normal ordered, we managed to make it into normal ordered of the entire thing times e to the phi minus correlation function, right? We're going to do exactly the same here. I've forgotten this. Yes. Epsilon. So if I put them together, I just have e to the minus I minus x minus phi minus y, and then e to the power correlation function, normal order correlation functions between these two. This is again a result that we derived last lecture. So the correlation function between them we denoted by G minus. So that's a clarifying thing. So we write down. That was the definition for G minus, and we calculated this last time to get 1 by 4 pi beta square, where beta is the thing that appeared in the action, log epsilon by epsilon. So this is also a calculation from last week. So let's plug all of this in, and x and y are close to each other, so we will just Taylor expand y around x plus phi minus x y phi minus evaluated at x plus dot dot dot. The dot dot dots are of course going to be neglected, and then what we will have is from here phi minus cancels. We have this term, and then since y minus x is small, we'll expand the exponent also to linear order. So e to the I minus x y phi minus value of x is approximately 1 minus I x minus y dx phi minus x. So I changed it to x because there is the limit and so on. Alright, if I plug this in and plug this in here with the special value beta square equal to 1 by 4 pi, what we would have is this factor equal to epsilon by epsilon x minus y. And epsilon is small, so this epsilon will cancel with that guy, and to leading order you can evaluate this thing to be by 2 pi, this guy, and x minus y will cancel against x minus y for small epsilon. And I end up with this thing plus limit y by x I by 2 pi x minus y plus epsilon star. So we see that this thing blows up. If we did not do the point splitting, we wouldn't have a phi minus y here, we would just have a phi minus x here. What that means is that we would just have this term, right? This term we got because of the point splitting that we did. And this is the infinity that we saw even last time, when x and y at the same point, a composite operator blows up. Right. So to make sense of this, we do the standard thing. We do normal ordering on the Fermion side as well. What that means is that we will subtract out this infinite part when defining what this operator means. So we will define this operator to be the normal ordered version of that, which means that this is equal to that. In short, we have say that the minus normal order, mapping to 2 minus. In the similar way, we can do it for another fermion as well. We get exactly the same thing. All right. So we have found this and this. So we can simply find these two, and then we have the bosonized version of the current dynamic. So J0B maps to phi minus plus phi plus, right?
Why did you put the normal ordering around the sides?
That just means I'm going to just subtract off this bit.
Okay. Is that like normal ordering in the standard sense, or is that just another notation?
I think it's ultimately the same, but people use normal ordering in these two senses. That one sense is all the A daggers to the left, the other is subtract off this zero coinciding infinity, just like here. So this Green's function, you call it normal ordered Green's function because you subtracted off the infinity.
Okay.
Right. So J0 is nothing but 1/2 pi plus minus minus, right? So that's dx phi plus phi minus. If you remember from last week, phi plus phi minus was our phi, right? Where is it? So, whoa. Yeah. The phi over there, we decomposed into phi plus phi minus. So this is nothing but 1/2 pi. Now, J1 is from there plus minus minus. So it's 2 pi dx ordered and plus minus phi minus. Does anyone remember what this was from last week? I'm just going to state it. This was the dual phi. Just as a reminder, we showed that the phi had a dual scalar field which described exactly the same physics but with a different radius. That was called the T-duality, and the T-dual in terms of the chiral bosons was something like this up to a constant. And I'll just put the constant right here. D squared dx phi twiddle was beta squared phi minus minus phi plus. If you check notes from last week, you can see that. Let's recall T-duality. T-duality gave us this relation, 1/2 right, T-duality mapped this current, this was the current of the boson due to phi plus constant being asymmetry of the action, and this is the topological current of the dual boson, which is conserved for free because of the epsilon symbol. And T-duality mapped the shift current, as we call it, to the topological current of the dual boson. Why am I bringing this up? Just so that I can write, I can eliminate phi twiddle for phi. So I can just, from this I can read off beta square dt phi is 1/2 pi epsilon dx phi twiddle, and this is nothing but 1. So dx phi twiddle I can write as dt. So in short, I have this equal to minus, did I mess up something? Not sure at the moment. So I'm confused about a factor of 2 pi. Yeah, I'm confused about a factor of 2 pi now. I know that this is the result I want, but I cannot find it. Yeah, I got it. So this is what I was saying, 2 pi beta squared is phi plus phi twiddle. So I missed the factor of 2 pi there, because I already had a 2 pi. So then that is alright.
Before you continue, can you actually return to this limiting thing? I still don't really get how it goes away.
We just subtract it away by hand. Just like if you remember when we do canonical quantization of a scalar field, we end up with an infinite constant.
Yeah.
What do you do with it?
Throw it away? Okay. So, you know.
So that's normal ordered way. So you measure these things relative to
Yeah.
that infinity.
Mm.
Doesn't make much sense, but that seems to joke.
Alright.
So ultimately we have these two things for J, which can be packaged into one nice relation. The vector fermionic current is mapped to 1/2 pi epsilon mu phi. So it's not phi twiddle by the way. So this is the topological current of the boson itself, and we called it J mu minor. This has charges conserved because of topological reasons. Okay. Now, the interaction that we are interested in over there is forget about the mass term for now. The massless Serine model, I slash psi is G mu. I can map it to a boson theory with the action, and remember the free part mapped to a boson with a radius 1/4 pi. So I'll just plug in 1/4 pi for beta square. So I have half 1/4 pi square. And the current interaction just maps to, there's a minus sign over there, a minus sign over here, makes it a plus sign, G by 2 pi square, G square, or in other words, dx of 1/4 pi is G by 2 pi square, G square. So this complicated 4 Fermi interaction just become a free boson. This is a free theory, there is no interaction. With a radius that's not equal to the magic value. That's all. And if it's a free theory, we can evaluate all the correlation functions, and we already did it last week. So the massless Serine model, even naively you would think that we need perturbation theory to solve it, can be solved exactly. Any questions at this point?
How did you give this, can you go through the S boson step one more time? So, yeah, you just,
Yeah,
Yeah.
so this bit from last week we showed that is a compact boson theory, that's this with beta square equal to 1/4 pi, right?
right,
So that's this bit. And the G current, well, we showed the current is that. So current is that product that leads you to this. So the current interaction just becomes G times the bosonized version of the current interaction, which is just the d phi square with a constant that multiplies it.
and that phi is the big phi,
Yeah. That phi is the
Yep.
big phi.
right.
So if no one has a question, I will ask a question myself. So if we derive the bosonization for a free theory, why are we using it for an interacting theory? So I don't really have a clear answer. I asked David Tom and he gave me an answer. So I will try to explain the answer after doing QED2 as well, because it's the same question, and at least in that case I think I understand the answer better than in this case.
I guess I have a question. Can you go back again and then just map it to free fermion?
This theory?
Yeah.
No,
Okay,
fermion
because,
mapping only works for.
Oh, well, there was a beta square,
So let's do.
So, yeah, so wanna go ahead and do the massive Thuring case?
Yeah, that's exactly what I'm going to do.
Alright,
So let's add the mass. So the mass term, if you go up, the mass term is that, and this if you just write out, psi bar is psi dagger times gamma 0 and so on, you will get it to be minus psi plus the complex conjugate. And here it turns out that even if I don't do point splitting, I get nice answers. So let me not do point splitting here. well, you can and get the same answer. So psi minus dagger, remember, we mapped it to one order e minus I phi minus x to pi epsilon, and psi plus was mapped to look at this once, e to the minus I phi plus x. This again we do the same story. So we end up with 1 by 2 pi epsilon of e minus I phi minus plus phi plus e to the power the commutator between these two. The commutator between these two and a half. The BCH formula has a minus sign because I and I. Phi minus x phi plus and this commutator we derived last time, and I remarked that there's a special feature that we will need. So if you remember from last time, phi minus x phi plus y, we derived it to be minus I by 4 beta squared if x is not y, minus I by 2 beta squared if x is y. So this is where this extra bit is useful. So let's make use of that. So we have e to the minus 1 by 2, x and x are the same thing, so minus I by 2, and beta squared, remember, is 1 by 4 pi. 1 by 4 pi is equal to e to the I pi equal to minus 1. Now, had I used 4 beta square there, then I would have a 4 here. Then I would have e to the I pi by 2, which is an I. So that somehow is not the right answer. So, yeah.
Why do we not do point splitting for this one?
Yeah, you can do it, but get the same answer. Because this guy, this commutator do not diverge, it's a constant.
But if you take the limit as x goes to y, you get a different answer. If you evaluated x equals y.
That's true.
So if you take the limit as x goes to y, you get the same answer as if you didn't do this.
That's a good
Well,
point.
you know, the theta function thing.
Yeah, but then we get the wrong answer, right?
Do you get that answer?
Yeah, it would be an I. So the I somehow messes up.
You're saying that if we use a different definition of theta function, it messes the answer.
Yeah. That makes no sense to me, but yeah, I don't know.
Why doesn't it make sense to you? If we use different definition, we are ending up somewhere else.
Yeah, but theta function is a mathematical construct that I used in the middle. And as he was saying, if you do point splitting, I get a different answer too.
If you do point splitting, it's independent of your choice of the theta function at 0.
Right. So it will just be 1 by 4, right? 1 by 2 ever. So
Did we use theta function somewhere else and forgot about the definition?
that could very well be the case that I messed up stuff.
Also, not necessarily you missed that. Maybe it is somewhere like hidden that we use some stuff that we don't even realize that as theta function as foundation somewhere. I don't know.
That
Maybe
could
the
be the
change is
case.
that you get 8 there instead of 4 pi.
That could be the case, but I'm not sure. I was not able to find a way to get around this. So I leave it as a puzzle to all of you. So the ultimate point I want to make, or the physics point I want to make, is that psi bar psi maps to minus 1 by 2 pi epsilon, and phi minus plus phi plus is phi e to the minus I phi plus complex conjugate, which is e to the I phi, and this is nothing but cosine. It's equal to minus cosine phi by pi epsilon. So if we do the massive field model, then what that means is we have to add minus m pi epsilon cosine phi. So this model is known as the Sine-Gordon model. It's a parody for Klein-Gordon apparently. Yeah. So
epsilon is still here.
the epsilon is still here, yes. I can try to remedy it a little bit later.
I'm confused about units, because m over epsilon is dimensionless, right? Or no, it's not, sorry about that.
Yeah. Epsilon
Yeah,
is
epsilon
inverse
one.
mass. Yeah. Also, did I mess up sign? I messed up sign. There are two minus signs. Minus. Okay, so let's ask the following question. We did the bosonization, whatever. What does a fermion look like in the bosonized picture? So we answer this question. We answer the question, fermion bosonized picture by looking at the map between the currents. So we will make use of this.
I have a question here. So if we used I instead of -1, what would be the issue? We would just get sine of phi, something like that.
Yeah. Is that an issue? I'm not
Is
sure.
that an issue? I don't know.
Well, you can shift phi by units of 2 pi. If it was the case that you can shift it by units of pi.
I mean, can you just define like phi prime equals phi plus pi or something?
Yeah, that's possible, I think. Maybe that's the resolution, but people just seem to get it right away.
Yeah.
Alright. So if I have a fermion has a charge, U1 charge, and it will be charged under this vector current, and we can compute the charge by looking at the action of this operator, which is defined to be integral over the charge density, which is nothing but x, just like we wrote somewhere else. So let's imagine that we take a fermion with unit charge. Then that should map to a boson configuration with winding 1, right? So let's remind ourselves what Q wind was. Q wind is 1 by 2 pi Ex and J0 1, 2 pi's Ex 1 by 2 pi Dx phi. So that is 1 by 2 pi phi at plus infinity minus phi at minus infinity. So if we had a fermion with charge 1, that should map to a bosonic field configuration with Q wind equal to 1. What that means is that we want this to be 2 pi. That is, we need a field configuration where the value of the field jumps from one value to 2 pi plus that value when it goes from spatial minus infinity to spatial plus infinity. If I draw a picture, this is x and this is phi, and say this is 2 pi, I need something like this. It stays at say 0 from minus infinity to some point, then it jumps to 2 pi. This configuration has Q wind equal to 1, and this is called a soliton or a kink.
Well, it can do whatever it wants in the middle, right?
Yeah, it can do whatever it wants. But it turns out that if you exactly solve it, that's the solution.
Okay.
Which I will skip. So this is the lesson from here. A particle in the fermion picture maps to a soliton in the other picture. So this is a particle soliton type duality. The Bosonization duality is a particle soliton type duality. Apparently people have discovered this particle soliton duality in higher dimensions as well. And one of that people is Ed Witten. So it must be right. Any questions? The epsilon, right? So the remedy is, I did not write it down because I thought I would skip it. The remedy is to find the energy of the soliton, and all we are doing is a semi-classical type analysis, right? So we will make sure that the energy of the soliton is m by choosing epsilon in some way. So it's slightly unsatisfactory, but that's what people seem to do.
What are the units of phi?
What are the units of phi? Phi is dimensionless.
It is dimensional? Yeah.
I mean, dimensionless in the classical sense.
Is there just some, so this M is like a bare mass, right?
Yeah.
Something like that, so is there just some renormalization
Yeah.
arguments or something?
Yeah.
Okay.
Something like that, which I just skipped.
So, if M over epsilon is finite independent of epsilon, so independent of the cutoff, does the sign coordinate thing make sense, or does, the coefficient of the sign coordinate, potential have to change with the cutoff?
I think it has to change with cutoff. It runs, yeah, it has to run because, e to the I phi itself has some running, right? So cos phi must have some running.
No, I don't know, it
Yeah.
makes sense.
Alright. Any other questions?
Is there any reason to consider enforcing that QV be anything other than 1?
No, I can choose
Or
anything.
some integer?
Yeah,
Okay.
QV has to be an integer because it's quantized.
Alright, we did
Just like Q wind is also quantized, right? Because of topology. pages of notes, is it fine if I go through them?
Yeah.
Okay, let's solve QED2.
Just one more stupid question. So we did no perturbation theory, right?
No, it's completely exact, right? I mean, after
So-
this last term, it becomes a bit tricky.
You just comment, one of the facts that I've said before, because I read it, is that, you know, the standard model doesn't conserve baryon number at the, what is it, non-perturbatively or either it must be non-perturbatively, right?
I don't know that.
So I'm just curious, is there, how does, do you know if this analysis was applied somehow to that, to get that result?
This analysis is only in 2D.
Yeah, it is, but I mean, yeah, so, I mean, of course, but I don't know how else I've never seen how one demonstrates that claim.
I have not seen that either.
Okay, but right,
I mean, it doesn't mean that it doesn't exist. There could be an argument. It's just that I have not seen it.
yeah.
Maybe Diana.
Yes, yeah. What are the non-perturbative methods aside from lattice and semi-classics?
Is there anything? I don't know anything.
I can only vaguely remember some words Peter Arnold may have said, but I think it does have to do with some instanton.
That's also some semi-classical analysis.
Yeah.
The one non-perturbative method is ADS-CFT, but that only works for n equals 4 super Young's, not for normal Young's. So that's non-perturbative. That again is a duality of this kind. You map some theory to another theory, then work out things in the other theory. So let's move to QED2. So QED2 is, well, just QED, but in 2 dimensions. Psi. And let me not, yeah, let's do that. And D, remember, is the charge is being normalized here, so fermions will have charges in integer number instead of a multiple of E because I've normalized it in that way. Right. Now the interaction between electromagnetism and fermions is buried in here. As we can see, if you expand this guy out, we will have I psi bar E slash psi minus pi psi bar mu psi and this is nothing but this is nothing but j mu vector, and we have already done the hard work. We already know what this guy is. So let me quickly comment about perturbation theory as such. So E, if you count dimensions, turns out to be of mass dimensions, and if as E tells us about the strength of the electromagnetic field, if E is really small compared to the mass of the fermions, we can just do perturbation theory, right? So in the perturbation theory, you would have normal fermions and antifermions, and if I create a fermion-antifermion pair, I can try to separate them, and since we are in one spatial dimensions, electric field do not have much space to spread out, just a one dimensions. The electric field between the particle and antiparticle turns out to be a constant. So the energy buried in that field is proportional to the length between them. So the potential energy is proportional to the length between the fermions, and this is what you call confinement. So it turns out that in the perturbative region, this model is confined. But that was easy. We did not do anything special, we just need normal perturbation theory to understand what's going on. But the real problem is in the other region. When this is strongly coupled, you cannot do perturbation theory. In this region of parameters, it doesn't even make sense to talk about fermions and electromagnetic fields separately, because they are so strongly coupled that, I don't even know what the degrees of freedom in that regime of coupling constants is. So this is the same problem, for example, in QCD. When QCD is strongly coupled, we don't know what the degrees of freedom is from a theoretical point of view. We know that from experiments or lattice, I guess, the true degrees of freedom in the strongly coupled regime are hadrons, which are color neutral states like protons or pion. Pion is a hadron. I think so. Is that true? Right. Pion is QQ bar.
Yeah.
Right. So, but we don't know how to arrive at that from starting from QCD and doing a strongly coupled field theory, non-perturbative. Just like here, just like that, here in the strongly coupled, that means electromagnetic field is really strong regime, we can already kind of guess that the emergent degrees of freedom will be some neutral states. In the QCD case, it's color neutral. In this case, we will guess it to be charge neutral. But can we see that starting from this, can we derive that neutral degree of freedom? And it turns out that we can. And there's no points for guessing. We'll just use Bosonization to derive that. All right. So let's try to work in this region, strongly coupled. Well, it doesn't matter for the derivation, but let's keep in mind that that's what we want to end up with. And bosonize that model. But already all the work has been done. That's all there is to it. So if I bosonize, boson, of course the electromagnetic field stays because bosonization is for the fermion. Square. And the I psi bar d slash psi, not the big D, but the small d, is the free part with radius 1 by 4 pi. So that gives me 1 by 8 pi d phi square. So this becomes that, just like we did before. That became that. And then the current interaction just becomes it just becomes 1 by 2 pi epsilon mu d mu phi d mu. So that again is coming from this.
No mass?
Mass, okay, mass, we know what it becomes, right? So mass becomes epsilon. Right, so we will even go to the extreme case that mass is too small and I can ignore it. So, which is the case in, for example, QCD. In the QCD Lagrangian, the quarks, not the quarks, the gluons themselves are, oh, this is the fermion mass too. I said something wrong. Scratch that. Right, so, yeah, so this is the bosonized version of the QED2 Lagrangian. And this term, we can integrate by parts to get 1 by 2 phi, so mu, which is nothing but f01. Right? We just have f01 is the only non-zero component, non-zero independent component of the electromagnetic tensor in 2 dimensions. So in the end, we just have 2x 1 by 2p squared to 1 plus 5 by 2 pi f01 plus 1 by 8 pi d5 squared plus n by epsilon cosine phi.
You get an extra factor of 2 and going from f squared to f01 squared.
This one, right?
No, in the first term, the 1 over 2e squared f01 squared.
Yeah, there is an extra factor.
Okay.
Let me put a 4 over there.
4 over there.
Okay, so that's a 4. I don't want to. I mean, what Gary was saying that this is a 4. So f01, and f10 are both non-zero terms, but they are both equal. So 2 times that, so that makes it 15. But just that here, this should be a 4. Right. Alright, so in this action, the electromagnetic potential, or A mu, appears only in F. So we'll use that fact to integrate it out. We do the path integral over A, just like we did in the T duality lecture. But just to make things simple, we will assume that there are no holonomies and stuff like that. In simple words, we just put the theory on a line, so we don't have some iron or bomb type phases to worry about. So integrating this out becomes easy. I can just solve for the equations of motion and substitute it back in, because it's a Gaussian integral. Saddle point is exact. The equation of motion is nothing but solve it in such a way that, well, this thing is a constant, but I'll just set the constant to 0 for simplicity. So we will have f01 equals minus e squared by 2 pi, plug it back in. That is equivalent to just doing this. Plug it back in and then get S boson effective action to be this action has some immediate features that strikes out. One is this term. So when we wrote the compact boson theory, we did not write the term like this. Why? Because it broke the phi shift symmetry. Right? Phi going to phi plus constant, this breaks that. So somehow integrating over electromagnetic field breaks that shift symmetry. But there is a good reason for that. The reason is the other part of this map. So under bosonization, we had the vector current of the fermion map to the topological current of the boson. In the similar way, for the fermion, we had the axial current as well, if you remember, in the massless case. So this axial current is a symmetry only when mass is zero. Where's the mass? Mass of the fermion is zero. When mass is not zero, we don't expect it to be conserved anyway. But even in the case, let's take the case when it's to be zero for now. Had we worked out the details of what this axial current would map to, we would get J mu shift. So the axial current of the fermion is mapped to the J shift. But remember, in the first lecture, we saw that if you turn on an electromagnetic field, this axial current is no longer conserved quantum mechanics. That was the chiral anomaly. So what would that mean in the shift or the boson case? The shift current would not be conserved, then you would not have a shift symmetry. And that's what you're seeing here. This term explicitly breaks the shift symmetry, and that ultimately is related to chiral anomaly in the presence of the electromagnetic field. Right? And another thing, so if we start with mass to zero, that is, in the original theory we set the fermion mass to zero. But in the effective theory, or the final effective degree of freedom that emerges out of all this mess, by the way, this integral that we did, this path integral that we did not assume anything about the strength of the coupling, so this is valid even for strong coupling. So in strong coupling, we can just think of this as our equivalent action. And we see that for strong coupling, let's say mass is zero, super strong coupling, the effective degree of freedom is just one massive scalar field. So even if we start with a mass equal to zero in the fermion theory, the original theory, we end up with the mass is E squared by 4 pi squared. Even if we start with the massless theory of fermions, we end up with a mass gap. So this is the baby version of the mass gap problem. We've demonstrated that QED2 has a mass gap. Alright. The next is confinement. So how do you detect confinement? You inject test particle and antiparticle and see what's the force between them. But we already know that a particle is a soliton. And by the way, due to this term, let's skip. So particle is a soliton, and if you have a particle which is a soliton and far away an antiparticle, you have this region of phi not equal to zero, but derivative of phi can be zero. I can arrange for that by trying to separate them really far away. But if I separate really far away, d phi is 0 because this is a constant region, but this thing contributes to the energy of this configuration. And since E square is really high, if I try to separate them really far away, the energy of this configuration goes above the limit of pair creation. That's confined.
This phi squared term doesn't respect also the
Periodicity, right?
periodicity.
Right. That's again because of this. We assume no fluxes.
Oh,
the
okay,
electromagnetic
so this is,
Yeah, that's a special case. You can do it, where F01 is quantized or the electromagnetic field is quantized, then the periodicity is actually restored. But the shift symmetry breaking remains. So it just replaces this by, I think, the minimum of 5 plus 2 pi n or something like that, then it respects the symmetry. Squares. I guess it is something like that, but it still breaks due to the squaring, the shift being a symmetry.
What about this mass thing? So I understand, so I thought I was fine with it, but if we start with m equals 0 initially, right, we can just read off what the mass is here.
Yeah, this is the mass term, right?
Yeah, but then,
So the effective degree of freedom that you have in the theory is gapped.
okay. So there's an m in the original theory times cosine phi, but here we said, the mass is this term because it's 1/2 m squared phi squared, but in the original one, it's not even close to that.
The original one, that's
So-
the mass term, that's the
Oh.
usual mass.
Wait a second.
But this is the bosonized mass term.
So it's the bosonized mass term, so it is the boson's mass. It is in. So.
So the boson's mass in this case is this guy. This is an interaction.
Yeah, so the fermion mass would induce self-interactions.
Right. The fermion mass introduces self-interaction. But even if I did not had a fermion mass, I still would end up with a degree of freedom which is gapped.
Yeah, that's Mr.
even if you don't have an interaction, I guess, does, it looks like you still have a, because if I Taylor expanded that cosine, you get phi
You will
squared.
get a phi squared, yes.
Yeah, but
So,
it's
um,
The point is that even if you started with, massless fermions, you end up with a degree of freedom with mass. And there is this thing that to notice that if we have strong coupling, which means E is much greater than M, then the boson theory is simple to solve because I can ignore this ridiculous term and this is just a free theory, I can solve it. But on the other end, if I have weakly coupled, which means mass is really high than E, then the boson picture is really hard to solve. But the fermion picture in that case is easy to solve quite a bit. So bosonization maps strong coupling to weak coupling. So this is an example of so-called S duality. S stands for strong, weak.
that's usually the result in the ADS CFT correspondence. That's sort of
ADS CFT is also a strong weak duality.
right, but this one we got it through 1+1 analysis of fermionic theory. So, is there any correspondence between bosonization as a correspondence itself and ADS CFT as a correspondence?
Yeah, the correspondence is, where is it? So this is, for example, a correspondence.
But I mean,
Is this related?
ADS CFT,
Oh, this is not related to ADS.
it's not related, even though it achieves the same thing, sort of in that sense of strong and weak
It achieves
Duality.
strong weak duality,
Yeah.
but in a different way.
in a different way.
In ADS-CFT, you have a theory
Yeah.
in D dimension, then there's another theory in D plus one dimension.
Right, right.
So it's even different space, time dimensions, and different geometry.
So, but even though even though it achieves the same thing, there's
It
no
achieves
relation.
similar thing.
Alright, yeah.
So this is like the hadron.
Yeah, well, I don't know how to
The phi
actually
is the
think about
hadron.
phi. Is phi the hadron? Not really sure though. But phi is the only degree of freedom that's
Yeah.
there, which is a neutral thing in some sense. But phi itself is not what you would associate with a particle in the weakly coupled case. E to the I phi was the fermion or the electron, right? What corresponded to an electron was E to the I phi. But in the strongly coupled case, I don't think you can even think about electrons and electromagnetic fields separately because it's strongly coupled. Some new degree of freedom is what's observed, and that's
Right, just like there's no like quarks and gluons in real life.
only this real life.
They're fake.
So we solved the baby version of the $1 million problem. So if we can do this for QCD, then
There, okay.
So in this, we have confinement in both cases, the strong and weak couple.
yes,
So there's no like deconfined phase of
no,
two.
no. You can in a cousin model, if you try to do the abelian Higgs model instead of fermions, you can try to add a Higgs potential and try to make a deconfined phase by Higgsing and so on. But it turns out that even that phase is confined due to vortices. Maybe Josh will talk about it.
No.
Yes. Do you have any more to talk about, or if not, then can you explain the other end of the kink again? Whatever this picture is I'm looking at down there.
So this is a fermion that we saw. It has e to the I phi was the fermion, and that created something with topological charge 1, right? So this is at -0 and then it goes to 2 pi. Very, very, very far away, I have something that goes from 2 pi to 0. So its topological charge is -1. So that's an antifermion, right? So you have a fermion antifermion pair.
Oh, okay.
And you can try to separate them, but as you separate them in the phi space, you have a region of non-zero phi. So even if you manage to make d phi to be 0, due to the mass gap, action will be finite and it will exceed the energy will be finite and will exceed the pair production capability. So if you separate it too much, that's no longer the lowest energy configuration. In contrast to, say, a massive stirring model that we did, the Bosonization led us to here. And this model, if I start with a 0 mass thing, it's gapless. So I can separate fermion and antifermion any further I want to. There's no confinement for it. The reason, of course, you have confinement here is electromagnetism.
Right, exactly.
Third questions?
Is that it?
Yeah. Oh yeah, there's one more thing. That's this. I promised to answer the question, why can we apply bosonization in tracking theory as well, right? even though I promised I don't know the answer. So this is what David told me through an email. So he told me that a gauge theory in 2 dimension is asymptotically free, which means that if you run your energy scale to UV, this becomes a free theory. So I can just go to UV and bosonize and then flow back to IR. That makes sense. But what about the etheric model? Etheric model, I'm not really sure if it's asymptotically free. I think gauge theories in 2 dimensions are asymptotically free, but this is not a gauge theory. So the same argument kind of don't work. So that's the half answer. In this case, yeah, you can think of it like that. But
So
in this
does
case-
RG and bosonization commute? Yeah.
Let me say yes. Because David Tom says.
Okay.
Okay, that's the final.
Alright.
So, if anyone finds the reason